The Great Pyramid stands as a silent challenge to our modern world. How did ancient builders achieve such staggering scale without any of our technology? This video uncovers the lost engineering methods behind the world's oldest stone monuments. You will gain a new understanding of human ingenuity, one that redefines what you thought was possible thousands of years ago. We will explore how massive stones were moved across impossible distances and shaped with impossible precision. We will even investigate the controversial theories of forgotten sciences. By the end, you will see these ancient wonders not as relics, but as testaments to a knowledge we are only just beginning to comprehend. What does our own potential look like when we learn from the distant past? Stonehenge at sunrise is a humbling sight, its great stones catching the first light like monuments to a forgotten dawn. These are not the only sentinels. From the windswept moors of Europe to the fertile plains of Asia, similar structures of colossal stone began to appear more than 5,000 years ago. They represent humanity's first ambitious steps into the realm of permanent architecture, a global phenomenon that speaks to a shared, burgeoning vision. Archaeologist Colin Renfrew points out that such projects required more than just muscle. They demanded a sophisticated level of community organization, a society capable of planning, feeding, and motivating a workforce for projects that spanned generations. The very first step in this grand process was choosing the right material. Builders sought out incredibly durable stone types, like the local sarsen stones used at Stonehenge, a dense sandstone that could withstand millennia of weathering. This choice highlights a fundamental principle, the importance of resource proximity. How do you move a mountain, even a small one? You start by finding the mountain close to home. Once a suitable outcrop was identified, the initial quarrying began. Using nothing more than fire, water, and stone hammers, workers would fracture the bedrock, levering free multi-ton blocks. The conceptual leap here is staggering. How does a society without written plans, without detailed blueprints, collectively hold the vision for such a grand and enduring project? It suggests a knowledge passed down through demonstration and oral tradition, a shared mental architecture that was every bit as real as the physical one they built. This foundational understanding of community and material sets the stage for the true mystery, the seemingly impossible task of moving these giants across the land. The journey of a single stone from quarry to monument was a marathon of coordinated effort. The most fundamental method for moving these massive blocks was a system of levers and rollers. Imagine a team of workers using stout wooden poles to pry one edge of a multi-ton stone upward, just enough to slip a cylindrical log underneath. They would repeat this along the length of the block, gradually transferring its immense weight onto a series of these rollers. Once positioned, teams with ropes could then pull the stone forward, with workers constantly moving the logs from the back to the front as it advanced. It was a slow, rhythmic dance of leverage and motion. Ancient Egyptian reliefs vividly depict this process, showing colossal statues being pulled on sledges while a worker pours water onto the ground in front, acting as a lubricant to reduce friction. The physics is elegantly simple, transforming an impossible drag into manageable, incremental progress. But the true challenge was not just the physics, it was the logistics. How do you coordinate hundreds of people to pull in unison, to time the placement of rollers, and to maintain a prepared pathway for miles? Sites like Baalbek in Lebanon, home to some of the largest stones ever quarried, show evidence of these transport roads and even discarded rollers, offering silent testimony to the immense effort. This method required more than brute force. It demanded impeccable organization and communication. turning individual labor into a single, powerful machine. This basic yet brilliant system demonstrates that the first step to moving a mountain was understanding how to conquer an inch at a time. But moving the stones was only half the battle. The true artistry began when these rough giants reached the building site. Here, a master craftsperson would face a block of granite, armed with nothing more than a stone hammer and a copper chisel. Their goal was to transform this raw material into a perfectly shaped block, a process known as stone dressing. Every strike was deliberate, a controlled fracture that slowly chipped away the excess stone. The sound must have been a constant chorus of focused taps, a rhythm of creation that echoed across the site for years. This was not haphazard bashing, it was a deeply intuitive craft. The Egyptians, for instance, used even harder dolerite stone balls to pound granite surfaces, gradually grinding them down to an astonishingly smooth finish. Across the world, the Incas developed a different technique, pecking at the stone with handheld tools and then grinding the surface with sand and water to achieve their famous seamless joints. Modern materials science reveals the genius in this seemingly simple work. By striking the stone repeatedly along a specific grain, the artisan could guide the fracture, controlling the break with remarkable accuracy. This required an intimate, almost spiritual understanding of the material itself. How does a person develop such a feel for stone? It speaks to a lifetime of training, where knowledge was passed from one generation of artisans to the next through careful demonstration and practice. The investment of time for a single block was immense, a testament to a culture that valued permanence and precision above speed. The walls of Machu Picchu stand as the ultimate proof of this skill. Their stones fit together so perfectly that not even a razor blade can slip between them, an interlocking puzzle that has withstood centuries of powerful earthquakes. This was not merely construction, it was a form of conversation with the very earth, a patient dialogue between human hands and ancient stone. This patient dialogue between hands and stone forms the bedrock of our understanding, yet whispers of a far more elusive art persist. Beyond the physical tools of levers and hammers lies a third, deeply mysterious method: the potential use of sound and vibration to manipulate massive stones. This idea emerges from the fringes of history, a speculative theory that ancient builders might have harnessed resonant frequencies to levitate or guide colossal blocks with seeming ease. Imagine a chorus of drums and trumpets, their specific tones causing a granite slab to lose its effective weight, becoming almost buoyant enough to be directed by a few individuals. Such accounts are rare and often lack verification, like the stories from explorer Henry Kjelsen, who reported Tibetan monks using instruments to lift stones. While these tales are not scientific fact, they invite us to explore a fascinating principle: acoustic levitation. Modern science confirms that specific sound waves can indeed suspend tiny objects in mid-air, creating nodes of pressure that counteract gravity. The question is whether this principle could be scaled to a monumental level, a technology now lost to time. The cultural context for such an idea is rich and widespread. Legends speak of Atlantis using vibrational science in its construction. Some researchers point to the Great Pyramid's inner chambers, noting their unusual acoustic properties, where certain frequencies create strange echoes and resonances. Were these chambers designed as amplifiers for a forgotten sonic technology, or are these stories purely metaphorical, representing a spiritual harmony between the builders and their materials? The line between myth and lost technology blurs here, challenging our perception of the past. It asks us to consider whether our ancestors discovered a fundamental relationship between sound, matter, and energy, a relationship we are only beginning to measure in our most advanced labs. The line between myth and lost technology is perhaps most clearly defined by the stones themselves, not in how they were moved, but in where they were finally placed. The heavens were the ultimate blueprint. Picture ancient astronomers on a windswept hill, their eyes fixed on the slow dance of the stars, meticulously marking the point on the horizon where the sun would rise on the longest day of the year. This was not mere stargazing, it was a form of cosmic engineering. At Newgrange in Ireland, a tomb older than the pyramids, a single narrow window above the entrance was engineered so that for just a few minutes at the winter solstice sunrise, a beam of light would travel down a long passage to illuminate the central chamber. This precise alignment required generations of observation to perfect. Similarly, at Chichen Itza in Mexico, during the equinoxes, the setting sun casts a shadow on the Great Pyramid that creates the illusion of a serpent slithering down the staircase. This fusion of architecture and astronomy served a dual purpose. Practically, these celestial events acted as a giant calendar in the sky, marking the seasons for planting and harvest. Spiritually, they wove the cosmos directly into the fabric of daily life, reinforcing cultural beliefs and connecting the community to the rhythms of the universe. How did they achieve such pinpoint accuracy without modern instruments? The tools were elegantly simple. A basic gnomon, a vertical pole stuck in the ground, could trace the sun's path by the movement of its shadow. By observing the extremes of these shadow paths over many years, builders could identify the solstices with remarkable precision. Alignment poles set in the ground at key sightlines would then lock in these celestial events, transferring the knowledge from the sky directly to the building site. The case of Stonehenge's heel stone is a perfect example. On the summer solstice, an observer standing at the center of the stone circle would see the sun rise directly over this massive, outlying stone, a dramatic effect that required foresight and planning spanning decades. This encoding of complex astronomical data into stone and earthwork represents a profound intellectual leap. It demonstrates a society capable of long-term collective thought, one that saw no separation between the science of the heavens and the symbolism of their faith. The monument was not just aligned with the cosmos, it was a permanent conversation with it. These walls are a geological jigsaw puzzle solved without a guiding image. The breathtaking ramparts of Sacsayhuamán in Peru are a masterclass in this enigmatic style, known as Polygonal masonry. Here, massive stones of wildly irregular shapes are carved to fit their neighbors with such perfection that the seams between them vanish. This was not a random stacking of rocks. It was a highly sophisticated engineering system designed for one of the most seismically active regions on Earth. The Incas and their predecessors across the Andes developed this technique to an astonishing degree, creating structures that have shrugged off powerful earthquakes for centuries. The core principle is one of interlocking strength. Unlike a wall of uniform bricks which has straight, continuous lines of weakness, a polygonal wall is a single, monolithic entity. Each block is locked in place by the unique shapes of the blocks surrounding it, above it, and below it. When the ground shakes, the energy from an earthquake is not concentrated along a straight crack. Instead, it is dissipated and redistributed throughout the entire wall as the stones shift and settle minutely against one another, only to settle back into their original positions once the tremor passes. It is a structure that dances with the earth rather than fighting against it. How did ancient artisans achieve such a perfect fit without modern measuring tools? The process began with selecting a rough stone from the quarry. A master builder would then use simple bronze tools and harder stone hammers to begin shaping it, not to a predetermined size, but to match the negative space left by the stones already in place. This was a patient, iterative dance of trial and error. A stone would be lifted into position, and the points of contact would be marked. It would then be lowered, and those high spots would be carefully pecked away with a tool. This cycle of lifting, testing, and carving would be repeated dozens, perhaps even hundreds of times for a single block. The final stage involved fine-tuning the fit using sand and water as an abrasive, grinding the surfaces together until they achieved that legendary seamless joint. At the site of Ollantaytambo, we see walls that have stood firm for over half a millennium, their stones still perfectly interlocked despite the constant tectonic pressures. This method required more than just skill. It demanded a profound, almost intuitive understanding of geometry and structural mechanics. What knowledge allowed the Incas to see the final, perfect wall within a chaotic pile of raw stone? It stands as a silent testament to a form of problem-solving that viewed resilience not as a battle against nature, but as a deep and harmonious collaboration with it. The granite bedrock of Aswan holds a story of immense ambition, a testament to the very first cut. Here, ancient Egyptian artisans did not merely carve stone, they convinced the earth itself to release its treasures. Their primary tool for this delicate negotiation was a clever application of simple physics, using wooden wedges and water. Workers would first identify a natural fracture in the granite, then chisel out a line of holes along this perceived weakness. Into these holes they hammered dry wooden wedges. Next, they saturated the wood with water. As the wedges swelled with moisture, they generated tremendous, sustained pressure, enough to propagate a clean crack through the incredibly hard rock. This method reveals a profound understanding of geology, an ability to read the stone and exploit its inherent planes of weakness. The entire quarrying process was a masterclass in planning and resource management, the unsung foundation of every great monument. At the Aswan quarries, the evidence is still breathtakingly clear. The unfinished obelisk, still partially attached to the bedrock, provides a perfect snapshot of this operation frozen in time. This colossal stone, which would have been the largest obelisk ever erected, shows the channels cut around its perimeter by workers using simple stone balls. Seeing its enormous scale, one cannot help but wonder, how did they plan to lift such a thing? But the first and more pressing question was always, how did they ensure a block this size did not crack during its very extraction? The answer lay in a meticulous process. Quarry masters had to possess an intuitive grasp of tensile strength, knowing how much stress the stone could withstand before it fractured unpredictably. Geologists note that different rocks have different internal structures, and the ancient tools were perfectly designed to work with these properties, not against them. Fire was another powerful ally. In other cultures and sometimes in Egypt, workers would heat the surface of a rock with a large fire, then rapidly cool it by dousing it with water. This thermal shock, known as spalling, causes the outer layer of the stone to flake off, effectively weakening it for further work. The organization of labor was as crucial as the engineering. Teams worked in coordinated shifts, with some cutting channels, others driving wedges, and others managing the constant supply of water and tools. This was not a chaotic effort, but a continuous, rhythmic progression. The quarry was a factory floor under the open sky, where the raw material of a civilization's memory was patiently, skillfully won from the earth. This foundational step, from the first wedge to the isolated block, underscores a universal truth about these ancient projects. Their grandeur was not born from magic, but from a deep and patient collaboration with the natural world, a conversation that began with listening to the stone itself. The walls of the Great Pyramid seem to be made of solid, quarried limestone, a fact we have taken for granted for centuries. But what if that assumption is wrong? A radical theory proposes that the pyramid's massive blocks were not cut and hauled, but poured. This idea of an ancient, advanced concrete suggests the builders used a form of geopolymer, a manufactured stone mixed on site and cast directly into place. Researcher Joseph Davidovits championed this view after conducting chemical analysis on samples from the pyramids. He found mineral compositions and air bubbles that are more consistent with a man-made reconstituted limestone than with naturally formed rock. The proposed recipe was deceptively simple. It could have used crushed limestone, a type of clay called kaolinite, and natron, a naturally occurring salt. Mixed with water, this slurry would have been a thick, workable paste that could be carried in baskets and poured into wooden molds. Over days or weeks, a chemical reaction known as geopolymerization would cause the mixture to harden into a block as durable as any quarried stone. The advantages of such a method are profound. It would dramatically reduce the need to transport multi-ton blocks, replacing that backbreaking labor with the movement of crushed material and liquids. It would also allow builders to create blocks of perfectly uniform size and shape, or even form complex, interlocking geometries that would be nearly impossible to carve from solid rock. How do we test such a provocative idea? Look to other sites. At Tiahuanaco in Bolivia, some of the massive stones have features that puzzle traditional archaeologists, including unusual surface textures and seemingly molded edges. Could these be the echoes of a lost casting technology? If true, this theory does more than explain how the pyramids were built. It challenges our entire perception of ancient innovation. It suggests a knowledge of chemistry and material science that we did not believe existed for another several thousand years. Were the greatest stone monuments in the world actually the first sophisticated concrete structures? The answer remains locked within the stones themselves, waiting for us to ask the right questions. Beneath the grandeur of every stone giant lies a hidden world, an unseen foundation that has borne its weight for centuries. While our eyes are drawn upward to the towering walls and soaring pillars, the true genius of ancient engineering often lies beneath our feet. In the Indus Valley, the city of Mohenjo-Daro was laced with a sophisticated network of brick-lined drains and channels, a subterranean system designed to manage water flow and protect the city's massive platforms from erosion. This was not an afterthought. It was the first and most critical step in any major project. Before a single stone was set, ancient engineers had to become intimate with the land itself. They would assess the soil's stability and understand the rhythm of the water table, reading the earth like a map to predict its behavior. This foundational work, often invisible in the final monument, was the key to its immortality. Geoarchaeologists studying sites from Rome to Mesopotamia find a common thread: the deliberate use of layered materials to create a stable base. A foundation trench would first be filled with a layer of compacted gravel, followed by sand, creating a capillary break that prevented groundwater from wicking upward and damaging the stonework above. This was a simple yet profound application of basic physics, using nature's own materials to create a permanent, dry platform. The design of the foundation itself was equally ingenious. For massive structures, builders often used stepped or pyramidal foundations that splayed outward underground, effectively distributing the immense weight of the walls over a wider area of soil. This prevented uneven settling, the silent killer of so many large constructions. How did they ensure these subterranean fortresses would last? Waterproofing was paramount. In Mesopotamia, builders used thick layers of bitumen, a natural tar, to line their foundations and drains. The Romans, in their aqueducts and temples, sometimes went so far as to use sheets of lead to create impermeable seals, a testament to their relentless pursuit of durability. The Parthenon in Athens stands as a masterclass in this holistic approach. Its foundation is not a rigid slab, but a complex, multi-layered base designed to move with the earth. When earthquakes have shaken the Acropolis, the temple's flexible foundation has allowed it to sway and settle without shattering, a dance with tectonic forces choreographed over 2,000 years ago. This behind-the-scenes work required a long-term perspective that is almost unimaginable today. These engineers were not just building for their own time, they were building for a future they would never see. How did they anticipate environmental threats they might only witness once in a lifetime? It speaks to a culture of accumulated knowledge, where observations of floods, landslides, and tremors were passed down and encoded into engineering principles. The true monument was not just the stone we see, but this deep, enduring conversation with the very earth it stands upon. A colossal stone block inches its way upward, not through flight or magic, but along a carefully engineered earthen highway spiraling into the sky. This is the reality of the ramp, the most widely accepted solution to the great puzzle of vertical lift. To raise millions of stones to the summit of the Great Pyramid, ancient engineers designed extensive ramp systems that turned the impossible slope into a manageable, if arduous, climb. These were not simple inclines, they were monumental feats of logistics in their own right, built from the very desert itself using mud brick, limestone chips, and plaster. Egyptologist Mark Lehner's work at Giza reveals the scale of such an operation, where the ramps would have required as much material as the pyramid's inner core, a temporary mountain built to create a permanent one. The design of these ramps was critical, balancing the need for a gentle enough slope for teams to pull heavy sledges against the sheer volume of material needed to build the ramp higher. A straight ramp reaching the pyramid's apex would have been impossibly long and consumed staggering resources. This led to theories of more efficient zigzag paths running up one face, or the spiraling ramp that corkscrewed around the rising structure, its path maintained by a complex wooden framework. How many people did it take to drag a 2.5-ton block up such an incline? Calculations based on known physics and ancient depictions suggest teams of dozens, perhaps even hundreds, of laborers, their synchronized efforts guided by the rhythmic beat of drums and the calls of overseers. The evidence, while fragmentary, is compelling. At the Giza Plateau, archaeologists have uncovered the remains of ramp embankments and what appear to be post holes for a rope and pulley system that could have helped direct the sledges. The bent pyramid at Dosha offers a fascinating case study. Its unique change in angle partway up may have forced a sudden redesign of the ramp system, a permanent snapshot of ancient problems solving under pressure. What innovations made this possible? The use of hydrated clay as a lubricant on the ramp surface, a technique shown in tomb art, would have been essential. So too was the constant maintenance of the ramp's surface and the intricate choreography of teams moving up and down its narrow paths. This method reveals a profound truth. The greatest monuments were not built by overcoming nature with brute force, but by working with its principles on a breathtaking scale. The ramp was a temporary, sacrificial structure, its eventual dismantling just as much a part of the plan as its construction, leaving behind only the perfect geometric form, a testament to the power of incremental collective ascent. A single carved stone placed upright in the earth is an act of profound faith. The immense labor of monument building was always fueled by something far deeper than engineering, a shared belief system that gave meaning to the generations of work. Consider Göbekli Tepe in Turkey, a site that predates agriculture by thousands of years. Its intricate T-shaped pillars, carved with animal spirits, were erected by hunter-gatherers, not a settled farming society. This turns our traditional understanding of civilization on its head. Archaeologist Ian Hodder suggests such a project required a powerful, unifying cosmology, a common spiritual purpose that could motivate people to come together, to contribute their labor, and to sustain the vision over lifetimes. The monument itself was the catalyst for community, not the other way around. The designs were saturated with symbolic meaning. The specific number of stones in a circle, the alignment of an entrance with a star, the choice to carve a wolf or a vulture, all of these choices were chapters in a cultural story, a physical representation of a people's mythology and their relationship to the unseen world. This spiritual impetus was often intertwined with political power. In ancient Mesopotamia, kings erected towering stone stelae inscribed with their deeds and likenesses, asserting their divine right to rule and their role as intermediaries between the people and the gods. The monument became a permanent declaration of authority, a fusion of stone and statecraft. A powerful case study lies on the remote shores of Easter Island. The creation of the massive Moai statues was an immense undertaking that defined the island's society. The process of quarrying, carving, and transporting these figures was not just a technical challenge. It was a sacred ritual that reinforced social cohesion and honored ancestral lineages. The entire community had a role to play, binding them together in a common, spiritually significant endeavor. Why would a society pour so much of its energy and resources into such a permanent, demanding project? The answer lies in the human need to create meaning, to connect with the cosmos, and to leave a legacy that would echo long after individual lives had passed. The stone was not just a building material, it was a vessel for memory, for belief, and for the very identity of a people. Understanding this powerful why completes our picture of the how, revealing that the true secret behind these ancient wonders may not be a forgotten machine, but a forgotten state of mind, a collective will forged in shared belief. A river's current can carry a burden that would break the backs of 1,000 laborers. For ancient engineers, waterways were not obstacles but open highways, offering a solution to their most daunting challenge. The seventh method, the strategic use of water transport, turns the landscape itself into a partner. Envision massive blocks of stone, each weighing many tons, securely lashed to enormous log rafts or bundles of reeds, floating serenely down a river. The water's buoyancy does all the heavy lifting, transforming an impossible overland haul into a manageable, almost graceful journey. This was not a rare technique, but a cornerstone of logistics for cultures blessed with rivers or coastal access. At sites like the Karnak stones in France, where thousands of massive standing stones form enigmatic rows, researchers note the proximity of old river channels and coastal inlets. The most plausible explanation is that these monoliths were floated on rafts during seasonal high waters, guided to their final resting places by teams in smaller boats. The physics is beautifully straightforward. A well-constructed raft displaces a volume of water equal to the weight of the stone it carries, allowing the river itself to bear the load. Maritime archaeologists point to evidence of ancient harbors near quarry sites, where stones could have been loaded directly onto vessels. In Egypt, the transport of obelisks provides a masterclass in this aquatic engineering. Workers dug extensive canals directly from the Nile to the base of construction sites, allowing these needle-like giants to be floated right to their foundations. How did ancient navigators manage such a precarious cargo? The engineering of the raft was paramount. Builders had to create a platform wide and stable enough to prevent a top-heavy stone from capsizing the entire assembly. This likely involved lashing multiple layers of logs together and carefully calculating the center of gravity before the stone was even levered aboard. The journey itself was a feat of coordination, using the natural current where possible, while teams on shore or in towboats guided the raft with long ropes, navigating bends and avoiding sandbanks. Seasonal floods were not feared but harnessed. their raised water levels providing the necessary draft to float stones through shallower channels. This method highlights a profound innovation, the ability to see the landscape not as a static challenge, but as a dynamic system of forces that could be understood and utilized. It represents a dialogue with the environment where human ingenuity learned to ride the very currents of nature to achieve the impossible. A master builder stretches a knotted cord, and the perfect right angle of a temple foundation emerges from the earth. This simple tool, a rope with evenly spaced knots, could generate a perfect 3-4-5 triangle, applying the Pythagorean principle over 1,000 years before the Greek philosopher was born. This was not isolated genius, but a shared, practical geometry embedded in the very fabric of ancient construction. The precision we see in these monuments was born from a suite of elegant tools. The Egyptian cubit, a standardized unit of measure based on the length of a forearm, was meticulously maintained and replicated, ensuring every worker from quarry to construction site was building to the same exact scale. For surveying vast landscapes and aligning colossal structures, engineers used instruments like the groma, a simple cross of wood that could sight straight lines and perfect right angles across miles of terrain. Researcher John Anthony West highlighted the staggering geometric harmony of the Great Pyramid, a structure not only aligned to the cardinal directions with an error of less than a fraction of a degree, but one whose base perimeter divided by its height yields a close approximation of 2 times pi. How could such accuracy be achieved with such basic technology? The answer lies in an iterative process of observation and refinement. To find true north, ancient surveyors might have tracked the circular path of a single star around the celestial pole, marking its extremes to pinpoint the center. They used the sun's own shadow, tracing its arc with a simple vertical pole to determine east and west with breathtaking accuracy. This knowledge was not confined to a secretive priesthood. It was a communal, living tradition. The principles of geometry and measurement were passed down through hands-on demonstration, learned by doing, and perfected through a lifetime of practice. A single master builder carried generations of accumulated understanding in his mind and muscle memory. The Parthenon in Athens stands as a sublime case study in this encoded mathematics. Its design is a play of perfect proportions where the ratio of its length to width and the spacing of its columns all reflect the golden ratio, an aesthetic ideal of balance and beauty that the Greeks found in nature. This was not merely decoration, it was a philosophical statement carved in stone, a belief that the universe itself was ordered by mathematical principles. How was this profound knowledge transmitted across centuries without widespread literacy? It lived in the rhythmic swing of a plumb bob, the taut pull of a measuring cord, and the shared vision of a culture that saw numbers not as abstract concepts, but as the sacred language of the cosmos itself. Fire was a quiet, powerful ally in the hands of ancient stoneworkers. In quarries and mines from the Roman era back to the deep prehistoric, builders used a clever technique of heating stone with fire and then rapidly cooling it with water. This thermal shock, known as spalling, causes the outer layer of the rock to fracture and flake away. It was a form of controlled persuasion, letting the natural properties of the material do the hard work of breaking itself. For extremely hard stones like granite or flint, this method was revolutionary. It dramatically reduced the endless, exhausting labor of pounding away with stone hammers, allowing workers to channel fractures along desired lines and extract large blocks or valuable nodules with far greater efficiency. Experimental archaeologists have recreated this process, finding that a carefully managed fire could raise the surface temperature of a rock face to several hundred degrees. When water was then thrown onto the superheated stone, the sudden contraction created immense stress, propagating clean cracks through the material. This was not a haphazard bonfire, it was a precise application of thermal engineering. The type of fuel was critical, with dense, hot-burning charcoal being a preferred choice for its ability to sustain intense, focused heat. Safety was managed by clearing the area of flammable material and carefully controlling the size and duration of the burn. Of course, the method had its limitations. An inexperienced worker could apply too much heat, causing the stone to shatter unpredictably rather than fracturing cleanly. It took generations of accumulated knowledge to understand how different types of stone would react, learning to read the sounds of the heating rock and the visual cues of its changing color. The Neolithic flint mines of Grimes Graves in England offer a powerful illustration. Here, deep shafts were sunk into the chalky earth to reach the precious black flint layers below. At the bottom of these narrow pits, miners would light small fires against the flint seam. After heating the rock, they doused it with water, causing it to crack and reveal the high-quality nodules within, which could then be pried loose with antler picks. The environmental impact of this practice, repeated over centuries, was localized but significant. Vast quantities of wood were consumed, potentially altering the landscape around major quarrying sites. Yet this very consumption speaks to the immense value these cultures placed on obtaining the perfect stone. This was not an act of carelessness, but a calculated trade, a willing transformation of the immediate environment to create something intended to last for eternity. The technique represents one of humanity's earliest and most intuitive partnerships with a fundamental force of nature, harnessing expansion and contraction to reshape the very bones of the earth. A temple carved directly into a cliff face does not conquer the landscape, it becomes an extension of it. This profound integration is the final, masterful layer of ancient engineering, where the monument and its environment were conceived as a single, unified entity. At Petra in Jordan, the famous treasury is not built upon the rock, but is sculpted from it, its ornate facade emerging from the living stone of the canyon wall. This approach required builders to adapt their grand designs to the immutable features of the existing topography, using natural contours for structural support and symbolic power. The placement of Machu Picchu is the ultimate expression of this philosophy. The city's structures flow along the ridge of a mountain, echoing the shapes of the surrounding peaks and embracing the curves of the Urubamba River below. It was a deliberate act of architectural harmony. Landscape archaeologists note that this was far more than an aesthetic choice. It was a physical manifestation of cosmological beliefs. In the Andes, mountains were not just landforms, they were sacred deities or apus. Building in concert with these powerful entities meant weaving human creation into the sacred order of the world. How did they plan such an organic fusion? The initial surveying was an intimate dialogue with the land. Before any stone was set, master planners would walk the site for months, observing the path of the sun, the direction of the winds, and the flow of water during rains. They used simple yet effective tools to map the terrain, perhaps using filled water channels to find level or marked chords to measure slopes, internalizing the very personality of the place. This deep reading of the landscape directly influenced the engineering. To stabilize steep slopes for building, they constructed vast networks of terraces. These were not merely flat platforms, they were sophisticated retaining walls that prevented erosion, managed drainage, and created microclimates for agriculture, turning a precarious mountainside into a stable, living foundation. The orientation of every door and window was also carefully considered, not just for celestial events, but to frame a specific sacred peak or to capture a particular beam of light at a significant time of day. Even the pyramids of Giza, which appear as stark geometric forms against the sky, are deeply integrated with their environment. Their alignment to the cardinal points is perfect, but their placement also reflects a relationship with the life-giving Nile. The valley temples and causeways connected the pyramids to the river, symbolizing a journey from the realm of the living to the realm of the eternal, with the pyramids themselves representing the primordial mound of creation emerging from the desert plateau. This holistic design philosophy achieved two supreme goals. Functionally, it created structures of immense durability by working with natural forces rather than against them. Spiritually, it embedded the monument with layers of meaning, making it a permanent touchstone between the community, the cosmos, and the land they held sacred. The true genius was understanding that the most powerful foundation was not just stone and mortar, but a profound and respectful relationship with the earth itself. Stories whispered through the ages speak of stones that moved as if they were weightless, guided by chance or the touch of a sacred rod. This ninth method ventures into the most speculative realm of all, the possibility that ancient builders mastered forces like anti-gravity or tapped into the Earth's own unseen energy. In alternative history, these are not mere fables. They are interpreted as literal descriptions of a lost science, one that could manipulate gravitational fields or harness the planet's electromagnetic grid. While mainstream archaeology finds no verifiable proof for such technologies, the theoretical underpinnings are fascinating to explore. Physicist John Brandenburg has noted that, in theory, manipulating local gravity or creating acoustic force fields is not beyond the realm of physical law, though replicating such feats with ancient materials remains an immense challenge. The core idea often revolves around vibrational resonance, the same principle that allows an opera singer to shatter a glass. If a specific resonant frequency could be found for a massive stone block, could that energy be used to cancel out its weight, making it buoyant? Others point to the concept of ley lines, hypothetical alignments of ancient sites that some suggest could have been used as conduits for a terrestrial energy source, a kind of prehistoric power grid. These theories often point to anomalous objects as potential evidence. The Baghdad battery, a clay jar containing a copper cylinder and an iron rod, could have generated a small electrical charge. While most archaeologists interpret it as a vessel for storing scrolls, its design invites speculation about early experiments with electricity. A more modern example comes from the construction of Coral Castle in Florida. A single man, Ed Leedskalnin, claimed to have discovered the secrets that built the pyramids, and he single-handedly quarried and positioned massive coral blocks, each weighing many tons. When asked how he did it, he would only say he understood the laws of weight and leverage. Did he stumble upon a forgotten principle of physics, or was his a unique form of psychological persuasion? These tales exist in a space between myth and potential reality. They challenge us to consider the limits of our historical knowledge. Could these stories be the distant echo of a true, but now vanished, understanding of the world's fundamental forces? The answer remains just out of reach, a shimmering mirage on the horizon of human ingenuity. The true monument was not the pyramid, but the society that built it. Beneath the shadow of these stone giants thrived a complex, living machine of human cooperation, an organizational feat that rivals the engineering itself. At Giza, the remains of worker villages tell a story far removed from the old tales of oppressed laborers. These were structured communities with bakeries producing thousands of loaves, barracks for housing, and infirmaries for care. Archaeologist Zahi Hawass and his teams uncovered evidence of a system managed with bureaucratic precision, where scribes meticulously recorded daily rations of bread, beer, and fish, tracking the immense logistics required to sustain a permanent workforce. This was not slavery, but a form of civic duty, a rotational service that drew from villages across Egypt. How do you motivate thousands of people to commit to a project they will never see finished? The answer lay in a carefully managed system of incentives and social structure. A clear hierarchy defined the worksite, from the chief overseer and master architects down to the skilled stonemasons and the teams of quarrymen and haulers. Seasonal labor was key, utilizing farmers during the Nile's annual flood, when their fields were underwater and their labor was available for national projects. These individuals were compensated with food, oil, and cloth, a form of payment that supported their families and integrated them into the economic heart of the kingdom. Participation was also framed as a religious and patriotic act, a service to the pharaoh and the gods that promised spiritual rewards. This model of large-scale organization was perfected by the Romans, who applied a military-style structure to civil engineering. The construction of their vast aqueducts was managed like an army campaign, with legions of soldiers and dedicated engineers divided into specialized units for surveying, excavation, and masonry. This division of labor created incredible efficiency, allowing for the simultaneous work on multiple sections of an aqueduct channel stretching for dozens of miles. How did these ancient managers avoid the chaos and discontent that could derail such enormous endeavors? They mastered the art of logistics and morale, ensuring a steady flow of supplies and a sense of shared purpose. The organizational charts of these projects were as vital as the architectural blueprints, a testament to a form of social engineering that understood how to unite human potential toward a single, monumental goal. A dry stone wall in the Scottish Highlands holds a quiet secret. Built without a single drop of mortar, it stands strong against the wind and rain for centuries, a testament to a universal and enduring craft. This art of dry stone walling and interlocking is one of humanity's oldest and most resilient engineering methods, found from the terraced slopes of the Andes to the mysterious Nurag towers of Sardinia. The principle is one of beautiful simplicity. Stability comes not from glue, but from gravity and friction, with every stone carefully chosen and placed to transfer its load to the ones below and beside it. A modern stonemason would explain the crucial role of hearting, the process of filling the internal gaps between the large facing stones with carefully selected smaller stones. This internal packing acts as a locking mechanism, preventing the larger blocks from shifting or wobbling over time, turning a loose pile of rock into a single, cohesive structure. The entire process begins with a patient sorting of the available stone. The builder must see the potential in each irregular shape, mentally cataloging them by size and form, always thinking several steps ahead about which piece will fit the emerging puzzle. Specialized tools aided this precision. Lifting tongs, a scissor-like tool, allowed a single worker to grip and maneuver heavy stones with control. Simple wooden gauges were used to test for gaps and ensure a consistently tight fit across the wall surface. Consider the Broch of Mousa in Scotland, a slender stone tower that rises over 40 feet into the air. For over 2,000 years, it has withstood the North Atlantic's gales solely through the perfect interlock of its stones. No mortar exists within its double-skinned walls, just skillfully placed rubble hearting that binds the structure into an immovable whole. What kind of knowledge was so vital that it had to be passed from one generation of builders to the next? It was a tactile wisdom, an understanding of balance and compression that could only be learned by hand. This method represents the essence of sustainable engineering, creating timeless strength from nothing more than the local landscape itself. A modern team of engineers stares at a 35-ton granite block, armed with nothing but ropes, logs, and sheer determination. This is the world of experimental archaeology, where theories about the past are tested not in books but in the dirt. These researchers build scale models and full-scale reconstructions. attempting to replicate ancient methods using only the tools that would have been available thousands of years ago. Their work has transformed our understanding from a list of possibilities into a lived, physical experience. For instance, in a project famously documented by the Nova series, a team attempted to raise an Egyptian obelisk using a massive earthen ramp and a system of levers. The experiment did not go perfectly, the obelisk nearly toppled, but that very failure was a success. It revealed critical, unrecorded details that ancient masters would have learned through hard-won experience, knowledge never written down but essential for survival. Engineer Mark Whitby has reflected on these projects, noting that the insights gained from what goes wrong are often more valuable than a smooth success. They expose the hidden variables, the small tricks of the trade that make the difference between a stable monument and a catastrophic collapse. The scientific process here is beautifully straightforward. It begins with a hypothesis, perhaps a specific type of rope configuration for pulling a sledge. Researchers then build the exact replica tools, from stone mauls to copper chisels, and put them to work under real-world conditions. They meticulously measure the force required, the wear on the tools, and the physical strain on the participants. This data either validates the theory or sends everyone back to the drawing board. Today, this hands-on work is often complemented by sophisticated computer simulations. Engineers can model the stress on a stone block as it is levered into place or calculate the precise wear patterns on a dolerite hammer pounding granite. This digital testing allows for thousands of virtual attempts, honing the most plausible methods before a single log is ever lifted in the physical world. A powerful case study comes from a Stonehenge transport experiment, where teams of volunteers dragged a concrete replica of a sarsen stone on a wooden sledge across a prepared track. The results were revealing. They demonstrated that on a slick surface of wet clay, a group of around 150 people could indeed move the massive stone at a walking pace. The experiment bridged the gap between a mathematical calculation and the gritty reality of mud, sweat, and coordinated chance. How do these reconstructions change our perception? They replace the abstract notion of ancient genius with the tangible image of human ingenuity, of problem solving through trial and error, of a knowledge written not on papyrus but in the calloused hands and shared effort of a community. A herd of oxen, their muscles straining against heavy yokes, could pull a load that would require hundreds of people. This 11th method, the strategic use of animal power, represents another layer of ancient ingenuity, where humans partnered with the strength of the natural world to achieve the impossible. From the powerful elephants of ancient India to the sturdy cattle of Mesopotamia, domesticated animals were integrated into construction sites as living engines, amplifying human effort on a colossal scale. Historians note that this was not a simple matter of hitching an animal to a sledge. It required generations of specialized knowledge in animal husbandry and training. Handlers had to understand the temperament of each beast, knowing how to command an elephant or direct a team of oxen with precise vocal cues and physical signals. This deep interspecies trust was as vital as any tool. The logistics behind this method were staggering. A large worksite employing dozens of elephants or hundreds of oxen needed a constant, massive supply of fodder and fresh water, creating a secondary industry of farmers and transporters dedicated solely to sustaining the animal workforce. The design of the harness was also critical. Ineffective yokes could choke an animal or rub its hide raw, rendering it useless. Cultures developed sophisticated padded collars and breastbands that distributed the immense pulling force across the animal's chest and shoulders, allowing them to exert their full strength without injury. The advantages were profound. Animals provided a consistent, renewable source of power, capable of working long hours in conditions that would exhaust human teams. They were especially effective for the long, steady haul over flat or gently rolling terrain, moving stone from quarries to riverbanks or along prepared causeways. Yet their use had clear limitations. Steep, rocky, or unstable ground was often impassable for large animal teams, requiring builders to revert to human-powered levers and rollers for the most delicate or treacherous sections of the journey. The bas-reliefs at Angkor Wat in Cambodia offer a stunning glimpse into this practice, depicting elephants, their great heads lowered in effort, hauling massive stone blocks for the city's legendary temples. These carvings are not just art, they are historical records of a complex logistical operation. How did ancient site managers mitigate the inherent risks of working with such powerful, unpredictable creatures? The answer lay in strict organization and profound respect. Elephants and oxen were valuable assets, and their well-being was paramount to the project's success. They were typically used in controlled, well-understood environments, with teams of human spotters and guides ensuring their path was clear and secure. This synergy between human intelligence and animal strength highlights a recurring theme in ancient engineering: the ability to see the entire ecosystem as a potential toolkit, where every resource, from a flowing river to a mighty beast, could be enlisted in the grand, collective endeavor of building for eternity. These silent stones hold more than the weight of centuries. They hold entire libraries of knowledge. For cultures that did not rely on written records, the monument itself became a permanent, three-dimensional archive, a form of architectural memory. The very layout of a stone circle or the proportions of a pyramid could encode mathematical constants, celestial cycles, and foundational myths, ensuring this wisdom would endure long after its creators were gone. Researchers like Graham Hancock have proposed that these structures might preserve advanced understandings of astronomy or even geology, observations so precise they challenge our timeline of scientific discovery. This was not merely decoration, it was a sophisticated system of data storage carved in stone. The evidence is etched into sites across the globe. In the temples of ancient Egypt, the axis of a hall might align perfectly with the rising of a specific star, like Sirius, whose heliacal rising heralded the annual Nile flood. The Pyramid of Kukulkan at Chichen Itza, with its 91 steps on each of 4 sides plus the top platform, creates a total of 365, a direct numerical representation of the solar year. This was knowledge made manifest, a calendar you could walk upon. The specific numbers chosen were never arbitrary. A count of 12 stones might reference lunar cycles, while a circle of 30 could symbolize the days in a month, turning abstract time into a tangible, countable object for the community. A profound case study lies on the small French island of Gavrinis. Its passage tomb, older than the pyramids, is covered in a mesmerizing tapestry of spirals, curves, and concentric circles. Some archaeologists interpret these intricate carvings not as abstract art, but as a potential star chart, a map of the night sky as it appeared thousands of years ago. What urgent message did these Neolithic builders feel compelled to preserve in such a permanent medium? Were they recording a rare celestial event or encoding a warning for future generations? This symbolic layer transforms our view of these sites from simple feats of engineering into profound acts of intellectual pursuit. The construction was not just about moving earth and stone, it was about freezing a moment of understanding, a snapshot of a culture's entire worldview, and setting it in the landscape for all time. A copper blade alone could not even scratch the surface of granite. Yet ancient workshops were filled with the steady, rhythmic sound of saws cutting through the hardest stone on earth. Their secret was not in the metal, but in the sand under their feet. This 12th method, abrasive cutting, transformed simple quartz and water into a precision tool more effective than any hardened steel. Workers would guide a soft copper saw along a marked line on a stone block, while assistants constantly fed a slurry of sand and water into the cut. Each pull of the saw pressed the sharp, angular quartz crystals against the granite, grinding away microscopic particles. The copper was merely a carrier, a way to deliver the real cutting force, which was the abundant, unyielding sand itself. Metallurgists point out that quartz, a primary component of common sand, ranks a 7 on the Mohs hardness scale, while granite is typically a 6 or 7. This simple fact of geology meant the abrasive was perfectly capable of scratching and wearing away the stone, while the copper, being much softer, remained undamaged and simply held the abrasive in place. The process was one of immense patience. Creating a deep cut in a massive block was not a matter of hours, but of days or even weeks of continuous, methodical labor. To ensure a perfectly straight cut, the saw was likely guided within a wooden frame or along a fixed track, preventing any deviation as the team worked in shifts, maintaining the relentless back and forth motion. The choice of abrasive was a calculated decision. While ordinary river sand was effective, crushed gemstones like emery or corundum, with their higher hardness, would have cut significantly faster, though at greater expense. The unfinished sarcophagi in the Serapeum of Saqqara stand as a perfect time capsule of this technique. Their polished surfaces are interrupted by deep, unfinished channels that bear the unmistakable parallel striations of long, straight saw cuts, a permanent record of the tool's path. How did these artisans maintain such consistency over such long and exhausting sessions? The answer lies in the system. A team would have developed a steady rhythm, perhaps guided by a chant or a drumbeat, turning a monotonous task into a coordinated, meditative practice. This method represents a profound kind of ingenuity, one that understood how to marshal the hidden strengths of ordinary materials to achieve the extraordinary. It was not about inventing a new, complex technology, but about seeing the potential for a powerful tool in the most common substance imaginable. The environment was not a backdrop for these monuments, but a co-architect. Ancient builders listened intently to the whispers of their local climate, turning potential threats into the very principles of their designs. In the high Andes, where freezing nights give way to thawing days, stoneworkers deliberately selected granite and andesite, dense igneous rocks less prone to the destructive cracking of freeze-thaw cycles. In the scorching deserts of Egypt, architects used the properties of local limestone and sandstone, materials with high thermal mass that absorb heat during the day and release it slowly at night, creating a more stable interior temperature. Geoarchaeologist Carl Butzer's work reveals how this deep environmental awareness dictated everything from the ground up. A site's very location was chosen based on soil stability and water table depth, with builders creating intricate drainage systems long before the first foundation stone was laid. This was engineering by adaptation, a dialogue with the elements. The iconic tapered shape of an obelisk is not merely aesthetic. It is a direct response to wind erosion, its form engineered to shed the force of prevailing gusts over millennia. In seismically active regions like the Aegean, the flexible, rubble-filled walls of Mycenaean tombs were designed to sway and settle during earthquakes, a brilliant answer to the Earth's unpredictable movements. This adaptive genius extended to interior comfort as well. The Indus Valley civilization built homes with strategically placed air vents to capture cool breezes, while the massive stone walls of medieval castles incorporated insulating materials like wattle and daub to retain warmth. A masterful case of this symbiosis is found at Mesa Verde. Here, the ancestral Pueblones constructed entire villages beneath towering sandstone cliffs. These natural overhangs were not random shelters, they were calculated choices. The cliffs acted as giant umbrellas, shielding the delicate mud and stone structures from snow, torrential rain, and the scorching summer sun, while the south-facing orientation captured precious winter light. How did ancient engineers consistently turn environmental constraints into lasting advantages? They saw the landscape not as an adversary to be conquered, but as a partner in creation. This profound respect for local conditions ensured their work would not just stand, but endure, speaking to a wisdom that understood true strength lies in harmony with the forces of nature. A simple wooden frame could lift a weight far beyond the strength of any single worker. This 13th method, the use of cranes and hoisting devices, represents a pivotal leap in ancient engineering, introducing mechanical advantage to the challenge of vertical ascent. While earlier cultures relied on ramps and sheer manpower, Greek and later Roman engineers perfected the crane, transforming the skyline of the classical world. The fundamental principle was the compound pulley, a system of multiple wheels that rerouted the force applied by a team of men or a single animal. By pulling a long rope through this system, they could multiply their effective strength, lifting massive stone blocks with a controlled, steady motion that ramps could never provide. Engineer and historian G. Landels describes how the Greeks likely developed the first true cranes from simpler frames, using them to place the intricate marble blocks of their temples with astonishing precision. The Romans then scaled this technology to an industrial level. Their most iconic innovation was the treadwheel crane, a massive wooden wheel powered by men walking inside it like a giant hamster wheel. This human-powered engine provided a continuous, reliable source of torque, capable of hoisting multi-ton loads to great heights. The materials themselves dictated the limits of this new power. The cranes were built from sturdy oak and elm, lashed together with iron fittings. Their ropes, woven from resilient hemp, were strong but set a firm ceiling on the weight that could be safely lifted before the fibers threatened to snap. The archaeological record preserves the ghost of these machines. On countless Greek and Roman stones, you can still find the nubs known as lifting bosses, small protrusions left on the stone where the tongs of a crane would grip. These were intentionally left rough, to be chiseled away and smoothed over after the block was set in place, leaving behind a permanent fingerprint of the construction process. The Colosseum in Rome stands as the ultimate testament to this technology. Its soaring upper levels, with their intricate arcades and seating, would have been impossible to assemble without a forest of cranes working in concert. Teams operating these machines on different levels could efficiently pass stones upward, building the amphitheater layer by layer in a carefully orchestrated ballet of leverage and labor. How did these devices evolve to meet the demands of ever grander projects? The answer lies in incremental improvements, the addition of more pulleys for greater force, the development of stronger rope-making techniques, and the use of counterweights to balance loads. This marked a profound shift in mindset, a move from conquering height with earthworks to mastering it with machinery. The crane was more than a tool. It was a declaration that human ingenuity could now reach for the heavens on its own terms. The silent resilience of ancient stone is now speaking directly to our modern world. We are witnessing a profound revival, where the very methods we once considered primitive are offering solutions to some of our most pressing engineering challenges. Structural engineer Peter James has spent years studying ancient monuments, not as ruins but as masterclasses in durability. He notes that the flexible, interlocking joints of Inca walls, which allow them to dance during an earthquake, are directly inspiring new designs for seismic-resistant buildings today. This is not mere historical curiosity. It is a vital transfer of knowledge across millennia. The core principle is passive survivability. building structures that can endure environmental stresses without complex technology or external power. In a world increasingly concerned with sustainability, ancient methods are experiencing a renaissance. The art of dry stone walling, for instance, requires no carbon-intensive cement and creates natural habitats for local species, making it an environmentally sound choice for modern landscaping and retaining walls. Similarly, rammed earth construction, a technique visible in foundations from China to the Middle East, is being re-adopted for its superb thermal mass, keeping interiors cool in summer and warm in winter with minimal energy consumption. This ancient wisdom is now being validated and refined by our most advanced tools. Digital modeling allows engineers to run countless simulations on virtual replicas of structures like the Parthenon, analyzing precisely how their unique foundations dissipate the energy of an earthquake. These digital autopsies reveal the hidden genius in the original design, principles we can now encode into the steel and concrete of our own cities. A powerful case study is found in the ongoing restoration of historical sites across Europe, where teams are deliberately abandoning modern mortar in favor of traditional lime-based mixes and repointing techniques. The reason is simple: the original methods have proven to last for centuries, while many modern repairs from just 50 years ago are already failing. What can we still learn from these age-old practices? Perhaps the most crucial lesson is one of perspective. Ancient builders worked in a long-term conversation with their environment, creating legacies meant to endure. Their ingenuity whispers a challenge to our own disposable culture, reminding us that the most profound innovations are often those that stand the test of time. The Moai of Easter Island stand as silent stone giants gazing inland from their coastal platforms. Their creation and journey represent one of history's most captivating engineering puzzles, a method born from the unique pressures and beliefs of a remote Polynesian society. Isolated in the vast Pacific, the Rapa Nui people developed a remarkable process to carve and transport these colossal figures. At the volcanic quarry of Rono Roroku, artisans used handheld picks made of hard basalt to slowly shape the soft volcanic tuff directly from the mountainside. Each statue began as a rough outline on the rock face, with workers carving deeper and deeper, eventually undercutting the figure until only its spine remained attached. The level of detail achieved with such simple tools is breathtaking. They would meticulously sculpt elongated noses, strong jaws, and sharp brow lines, often leaving the final, delicate carving of the eye sockets as the very last step before a statue was separated from the living rock. The quarry itself is a frozen moment in time. Dozens of moai in various stages of completion are still embedded in the slopes, from mere outlines to nearly finished figures, offering a perfect snapshot of this painstaking generational work. But carving the statue was only the beginning. The true mystery has always been how these multi-ton figures traveled miles across the island's rugged landscape to their final ceremonial platforms, known as ahu. For many years, the prevailing theory was that they were dragged horizontally on log sledges. However, a compelling alternative, championed by archaeologists like Joanne van Tilburg, suggests the moai were actually walked upright. This theory proposes that teams used a system of ropes to rock the statue from side to side, edging it forward in a controlled, upright shuffle. In experimental tests, relatively small groups have successfully moved multi-ton replicas using this method, demonstrating its physical plausibility. The logistics behind this effort reveal a highly organized society. Different clans on the island appear to have competed to erect larger and more impressive moai, a social drive that fueled ever greater engineering feats. This required a sophisticated division of labor, with some groups dedicated to quarrying, others to carving, and still others to the perilous task of transportation. How did this remote community sustain such an immense, ongoing effort? The answer lies in a cultural worldview where the Moai were far more than simple monuments. They were considered sacred embodiments of ancestral spirits, whose presence ensured the community's spiritual and physical well-being. The investment in their creation was an investment in life itself, a profound cultural drive literally set in stone. A single merchant's journey could carry an idea that would reshape a city's skyline. While we often picture ancient civilizations in isolation, they were in fact deeply interconnected by vibrant trade networks that moved more than just spices and silk. Along these routes traveled the most valuable cargo of all, knowledge. The blueprint for a new arch, the design for a stronger tool, or a novel solution for moving massive stones could spread from one culture to another, carried by merchants, diplomats, and artisans. Archaeologist Andrew Sherratt's research into these early exchange systems reveals that trade routes like the precursors to the Silk Road were not just economic corridors, but neurological pathways for the brain of early civilization, transmitting technological impulses across vast distances. The evidence is etched in stone itself. Look at the corbelled arch, a structure where each stone projects slightly beyond the one below until they meet at the top. This identical solution appears in the grand gateways of Mycenaean Greece and the fortified walls of the Hittite Empire in Anatolia. Such a specific architectural idea is unlikely to have been born independently in two neighboring regions at the same time. It strongly suggests a transmission of technique, a shared concept that traveled with traders and soldiers. This exchange was dramatically accelerated by the spread of metallurgy. The knowledge of bronze alloying, combining copper and tin, created tools that were far superior to pure copper for working stone. As this metallurgical knowledge spread, so did the capacity for more intricate carving and more efficient quarrying, elevating the ambitions of builders from the Nile to the Indus. But this was never a simple act of copying. When a new idea arrived, local builders became innovators, adapting foreign methods to their own unique materials and cultural needs. This process of integration created beautiful hybrid styles. A culture with abundant timber might adapt a stone lifting technique to use local hardwoods. A society that revered the sun might align an imported arch design to frame the solstice sunrise, infusing a practical structure with their own spiritual meaning. The Phoenicians, master seafarers of the ancient Mediterranean, offer a perfect case study. As they established trading posts from Lebanon to Spain, they brought with them advanced techniques for constructing artificial harbors, using hydraulic concrete and submerged moles to create safe havens in exposed locations. The ports of Carthage and other Phoenician colonies became hubs of this transferred engineering, which local cultures then adopted and refined for their own coastal cities. How did builders decide which outside ideas to embrace? The choice was likely pragmatic, guided by local challenges. If a new type of pulley made lifting local sandstone easier, it was adopted. If a foreign foundation design proved more stable in their clay-rich soil, it was integrated. This constant, slow-motion dialogue between cultures created a rich tapestry of engineering diversity. The monuments we admire today were rarely born in a vacuum. They are the legacy of a conversation that stretched across continents, a silent collaboration between distant minds connected by the dusty paths of ancient commerce. A stone ceiling can be built without a single arch, using only gravity and geometric precision. This is the principle of corbelling, a technique that created some of the world's first enclosed stone spaces. In structures like the Treasury of Atreus in Greece, builders achieved this by stacking concentric rings of stone, with each course projecting slightly inward over the one below. Slowly, painstakingly, the walls would curve toward each other until they could be capped with a single stone at the apex, forming a sturdy, self-supporting vault. This same elegant solution appears across cultures and continents, from the steeply angled corbelled vaults in Mayan temples to the massive, hidden roofs of Neolithic passage tombs in Europe. The stability of such a structure comes from its brilliant distribution of force. An architect would explain that the weight of each stone is not thrust outward, as in a true arch, but is channeled directly downward through the wall itself and into the foundation. The entire structure becomes a monolithic entity, its strength derived from this continuous, compressive load path. The construction demanded incredible foresight. Every stone in the corbelled sequence had to be cut with meticulous accuracy to maintain a consistent inward curve. A single miscalculation, one block projecting too far or not enough, could disrupt the equilibrium and compromise the entire vault. This limitation naturally restricted the width of the spaces that could be spanned, confining most corbelled structures to narrower passages and chambers. To achieve the necessary symmetry, builders likely used simple wooden templates or guiding frames. These templates would have provided a physical reference for the desired curvature, allowing workers to shape each stone to fit its specific place in the rising spiral. Once the structural work was complete, the interior surface offered a new canvas. The stepped, overlapping layers of stone could be smoothed over with plaster or left exposed, their raw, geometric pattern becoming a powerful decorative element in its own right. A masterful example of this method's endurance is the Newgrange Passage tomb in Ireland. Here, a corbelled roof has sheltered the inner chamber for over 5,000 years, remaining perfectly dry and intact through countless storms. How did these early builders, without formal mathematics, intuitively calculate the complex stresses within these stacked stone canopies? Their success speaks to a profound, hands-on understanding of load and counterload, an elegant solution for enclosing sacred space that relied on nothing more than the intelligent placement of one stone upon another. The landscape of ancient Britain was a canvas for a grand celestial map. Across the rolling hills, a network of stone circles and earthen mounds were not isolated creations, but points in a vast, coordinated design, each one aligned with the sun, moon, and stars. This shared orientation hints at a cultural project spanning centuries, a unified vision that connected communities across generations. The purpose of these alignments remains one of archaeology's most compelling puzzles. Were they sophisticated astronomical observatories, allowing priests to predict seasons and celestial events with uncanny precision? Or were they territorial markers, using the heavens to sanctify a tribe's claim to the land? Some researchers even propose they functioned as sites for harnessing terrestrial energies, their stones acting as conduits for forces we are only beginning to understand. The work of engineer Alexander Thom was groundbreaking in this field. After meticulously surveying hundreds of sites, he proposed that the builders had achieved a remarkably advanced understanding of geometry and astronomy. He suggested that certain stone alignments were used to track the complex 18.6-year cycle of the moon, pinpointing its most extreme rising and setting points, known as the major and minor lunar standstills. Modern studies have brought new tools to this ancient mystery. Researchers now use high-precision theodolites and satellite imagery to verify these alignments, mapping the sightlines from one monument to another with digital accuracy. These technologies confirm that the patterns are deliberate, not accidental, yet the story is not uniform. Cultural variations reveal different priorities. In the high desert of Peru, the vast Nazca lines are not aligned to the stars, but to geographical features on the horizon and sources of water, etching a sacred map of the earthly landscape visible only from above. A profound case study exists at Karnak in France. Here, over 3,000 standing stones stretch for miles in parallel rows, a monumental arrangement that defies simple explanation. The purpose of these alignments is still debated. Were they a processional pathway for rituals, a physical calendar, or perhaps a boundary for the community of the living and the realm of the ancestors? What unified vision could drive such a widespread and enduring effort? It suggests an intellectual landscape where the sky was not a distant void, but a living, integral part of human existence, and where building in stone was the ultimate act of joining that cosmic conversation. A perfect line of stone blocks, each one an exact duplicate of the next, hints at a process far beyond individual carving. This 16th method explores the provocative idea of molds and formwork, a system of mass-producing stone elements that could revolutionize our view of ancient construction timeline. At certain Roman sites, and even in some Egyptian contexts, archaeologists note rows of standard-sized blocks or decorative pieces that show almost no measurable variation. In a world of hand tools, such uniformity is statistically unlikely, pointing instead to a replication process. Construction historian Jean-Pierre Adam has pointed to the feasibility of using wooden or stone molds, into which a workable slurry of crushed limestone, sand, and a natural binder could have been poured. This mixture, a precursor to modern concrete, would then be left to cure and harden into a perfect replica, ready for use. The process itself was a masterclass in efficiency. A master mold would be carved with immense care a single time, perhaps for a complex cornice or a standard-sized block. This template could then be used over and over, producing dozens of identical elements simultaneously. The curing conditions were critical, requiring a controlled environment of steady humidity and temperature to ensure the chemical reaction, known as pozzolanic setting, created a stone of maximum durability. The advantages for a large-scale project are immediately clear. Speed of construction would increase exponentially, as teams no longer needed to hand-carve every single piece. Cost would plummet as skilled labor could be focused on creating the master molds, while less specialized workers managed the mixing and pouring. This system also allowed for the uniform application of intricate decorative details. A rosette or a fluted pattern could be cast directly into the element, eliminating thousands of hours of repetitive, painstaking carving. The Roman mastery of concrete formwork for structures like the Pantheon's dome provides a powerful parallel. They built massive wooden frameworks into which their famous volcanic ash concrete was poured, creating shapes that would have been impossible with cut stone. Could this knowledge have been applied earlier on a smaller scale for replicating individual blocks? If true, this method shatters the romantic image of every stone being individually hewn by a master mason. It suggests an industrial, assembly line mindset existed in the ancient world, where the goal was not just grandeur, but also breathtaking efficiency, leaving behind a silent legacy of perfect, identical stones. The perfect stone was not merely found, it was understood through generations of patient observation. Ancient builders possessed a sophisticated geological wisdom, reading the landscape like a living text to select materials that would defy time itself. This was not a matter of grabbing the closest rock, but a deliberate choice based on a deep, empirical knowledge of a stone's grain, its hardness, and its long-term behavior under the elements. Cultures like the Egyptians meticulously categorized their stones, as surviving texts indicate they differentiated between limestone varieties based on their workability and durability for specific tasks. They learned which stones could hold a sharp edge for carving hieroglyphs and which were best for the immense, load-bearing core blocks of a pyramid. This understanding was passed down through oral tradition and hands-on apprenticeship, creating an unbroken chain of practical geology. Geologist James Harrell highlights how this knowledge extended to the symbolic use of materials, noting that fossil-rich limestone was sometimes deliberately chosen for temple walls, its embedded sea creatures perhaps symbolizing the primeval waters of creation from their mythology. The testing methods were elegantly simple yet profoundly effective. A builder would strike a potential stone with a hammer. Listening to the ring it produced a clear, high-pitched tone indicated a dense, solid interior, while a dull thud might warn of hidden cracks or flaws. They also examined a stone's resistance to weathering by observing existing outcrops, seeing how the wind and rain had sculpted them over centuries. This led to the strategic use of different stones within a single structure. A foundation might use a rough, durable granite for its compressive strength, while the interior chambers employed a finer, more easily carved limestone for detailed relief work. The iconic Parthenon in Athens stands as a masterclass in this selective process. Its brilliant white marble was quarried from Mount Pentelicus, specifically chosen for its uniform fine grain, which allowed for the intricate sculpting of the frieze and its pure whiteness that would gleam in the Mediterranean sun. How did this empirical knowledge develop over countless generations? It was a slow accumulation of success and failure, of noticing which quarry produced blocks that cracked in the frost and which remained steadfast. This geological wisdom, born from a lifelong conversation with the earth, was the invisible foundation for every visible wonder, ensuring that the legacy they carved in stone would truly endure for the ages. A heavy stone can be made almost weightless with the right kind of balance. The 17th method, the application of counterweight systems, represents a brilliant leap in mechanical thinking. Imagine a massive stone block suspended from one end of a pivoting beam, while on the other end hangs a large container steadily filling with sand or water. As the counterweight grows heavier, it gracefully lifts the stone, allowing workers to nudge it into its precise final position with minimal effort. This principle, where a smaller, manageable force is used to control a much larger one, is the essence of mechanical advantage. While we have clear evidence of complex counterweight cranes from the medieval period, the seeds of this idea almost certainly existed in ancient times, particularly for the delicate task of adjusting multi-ton blocks in confined spaces where ramps were useless. A physicist would explain that the system operates on the simple yet profound calculation of moments. The force of the counterweight multiplied by its distance from the pivot point must equal the force of the load multiplied by its own distance. Get this ratio right and stability is assured. Get it wrong and the system fails. This was not abstract math, but a tangible reality understood through trial and observation. We can see the foundational concept at work in a simple but vital ancient device, the shaduf. Used for thousands of years for irrigation along the Nile, the shaduf is a long pole pivoted on a crossbeam, with a bucket on one end and a counterweight of mud or stone on the other. It allowed a single person to lift heavy amounts of water with ease. Is it such a stretch to imagine that the same minds who engineered entire civilizations would see the potential to scale this idea upward, to lift stones instead of water? The direct evidence from art or texts for such systems in deep antiquity is frustratingly scarce, as these were likely built from perishable wood and rope. Yet their ghost lingers in some of archaeology's most enduring puzzles. Consider the massive lintels at Stonehenge. How were these crosspieces, each weighing many tons, hoisted to the top of the standing trilithons? A ramp seems impractical for such a precise, elevated placement. A system of levers and counterweights, however, could have provided the controlled, incremental lift needed to walk the stone upward into position. a patient and clever solution. This method asks us to see ancient builders not just as masters of brute force, but as intuitive physicists. They learned to play with balance, to use weight against itself, turning the very burden of the stone into the means of its own conquest. A single archaeological discovery can shatter our entire understanding of the past. Recent excavations at Giza have unearthed a previously unknown tool workshop, a place where the very instruments used to shape the pyramid blocks were maintained and stored. This find provides a tangible link to the hands that built the wonders, revealing not just the tools themselves, but the organized industry behind their use. Inside, researchers found not only stone hammers and copper chisels, but also evidence of a sharpening station, where dulled tools were meticulously re-edged to continue their endless work on the limestone and granite. This workshop paints a picture of a continuous, highly specialized operation, a level of logistical planning we are only beginning to appreciate. Such discoveries are rewriting engineering history, forcing us to replace speculation with physical proof. The role of modern technology in these revelations cannot be overstated. At sites like Angkor Wat, LiDAR scans have pierced the dense Cambodian jungle canopy to reveal a sprawling, low-density urban landscape complete with canals and roads, a metropolitan grid that supported the temple's construction. This technology acts like an X-ray for the Earth, showing us the full context of a monument, not just the isolated structure. Space archaeologist Sarah Parcak uses satellite imagery to identify subtle discolorations in the soil, patterns that signal buried walls or forgotten quarries from hundreds of miles away. These tools allow us to see the ancient world not as a collection of isolated ruins, but as a connected, living civilization. One of the most definitive discoveries came from the Hatnub alabaster quarry in Egypt. Here, archaeologists uncovered a well-preserved ramp system flanked by staircases and post holes. This configuration provided the first direct, undeniable evidence for how workers hauled massive stone blocks up steep inclines. The post holes indicate a complex pulley mechanism, where teams operating on the stairs could use ropes wound around these posts to provide additional leverage, effectively walking the multi-ton sledges up the ramp. This is no longer a theory, it is a preserved moment in time, a frozen snapshot of ancient engineering in action. Further insights come from the microscopic world. Using high-resolution 3D scanning, researchers now analyze the faintest tool marks left on stone surfaces. The unique striations and fracture patterns can be matched to specific types of tools, revealing whether a surface was cut with a copper saw using an abrasive slurry or pounded smooth with a dolerite ball. This forensic analysis tells us not just what they did, but exactly how they did it, down to the angle of a craftsman's strike. Perhaps the most paradigm-shifting case is Göbekli Tepe. The excavation of this site in Turkey revealed complex, T-shaped pillars covered in intricate animal carvings, a project of staggering ambition. The stunning fact is that it was built by hunter-gatherers, a society that predated agriculture by thousands of years. This single discovery single-handedly demolished the long-held belief that monument building required a settled, farming society with a food surplus. It proves that the drive to create lasting stone monuments and the sophisticated social organization required to do so is far older and more fundamental to the human spirit than we ever imagined. What do these accumulating finds tell us about the pace of innovation? They suggest that technological leaps were not always slow and gradual. A project like Göbekli Tepe implies that a sudden, powerful convergence of belief and social will could trigger an engineering revolution, a burst of creativity that set a new standard for what was possible. Each discovery, from a humble tool workshop to a lost city revealed from space, peels back another layer of mystery. reminding us that the story of ancient engineering is still being written, one fragment at a time. The surface of a granite obelisk begins its life as a chaotic landscape of rough fractures. To transform it into a canvas for intricate symbols, ancient artisans employed a patient dialogue of impact and abrasion known as pecking and grinding. Armed with a hammerstone of even harder material like dolerite or quartzite, a craftsperson would begin a rhythmic tapping, using the pointed end of the tool to create a series of controlled, tiny fractures. Each precise strike chipped away a minuscule fleck of stone, slowly defining the outline of a hieroglyph or the curve of a ceremonial animal. This was not a hurried process. For a small ceremonial stela, the pecking alone could take many days, while a massive wall panel covered in detailed reliefs might require a team of workers laboring for months. The resulting surface was a textured field of small indentations, a ghost image of the final design waiting to be revealed. Once the basic form was fully pecked out, the next stage began, the grinding. Using a smooth, handheld stone of coarse sandstone and a slurry of water and fine sand, the artisan would patiently rub the pecked surface. This abrasive action wore down the sharp peaks between the indentations, gradually transforming the rough texture into a smooth, polished plane. The conservators who study these ancient inscriptions note that this two-stage process is precisely why the sharp edges of the carvings have survived for millennia. The grinding compacted the crystalline structure of the stone, creating a hardened, durable skin far more resistant to wind and water erosion than a freshly cut surface would have been. This universal technique appears in the deep-time rock art of Aboriginal Australia, where ancestral beings were pecked into cliff faces, and in the rune stones of Scandinavia. A masterful example is the Rosetta Stone itself. Its perfectly preserved Greek and Egyptian scripts, with their crisp, parallel lines and uniform depth, are a direct result of this meticulous method. How did an artist ensure the consistency of a complex design across such a vast surface? They likely began with a grid, sketching the design in red ochre or charcoal, a guide that was worn away by the grinding process, leaving behind only the permanent, pecked message. This was artistry measured in millions of tiny impacts, a testament to the human capacity to impose perfect order onto the most unyielding materials through a fusion of unwavering vision and painstaking effort. Every new discovery at an ancient site carries a hidden cost. The very act of unearthing a lost wall or a forgotten tool can begin its slow erosion, forcing archaeologists into a profound ethical balancing act. They must weigh the hunger for knowledge against the solemn duty to preserve these fragile wonders for the generations yet to come. This is the quiet challenge that defines modern engagement with the past, a responsibility that extends far beyond the thrill of excavation. At celebrated sites like Machu Picchu, the sheer volume of visitors presents a constant threat, where the tread of countless feet gradually wears down original stone pathways and alters the microclimate within sacred chambers. The issues are complex and layered, from the criminal looting that severs artifacts from their history to the slow, environmental damage caused by pollution and climate change. As heritage scholar Lynn Meskel notes, the most effective conservation efforts now prioritize the voices of local communities, recognizing that those closest to a site often hold the deepest understanding of its meaning and the greatest stake in its survival. To study these engineering marvels without causing harm, researchers increasingly turn to eyes in the sky and ears in the earth. Drones equipped with high-resolution cameras map vast areas in stunning detail, revealing patterns invisible from the ground. Ground-penetrating radar sends harmless pulses into the soil, painting a picture of buried foundations and chambers without ever breaking the surface. These non-invasive techniques allow us to read a site like a book without tearing out its pages. This careful approach fuels an ongoing debate in conservation circles, the choice between reconstruction and preservation. Should a collapsed column be meticulously reassembled, or left as a ruin that honestly speaks of time's passage? Each approach has its merits. Reconstruction can help us understand the original engineering and visual impact, while preservation maintains the authentic texture of age and the story of decay. The Acropolis in Athens stands as a global case study in this delicate balance. Its ongoing restoration is not an attempt to make the Parthenon look new, but a painstaking intervention to stabilize its structure for the next millennium. Each original marble block is documented, analyzed, and when necessary, supplemented with new marble that is distinguishable yet harmonious. This work, guided by international treaties and shared cultural values, is a form of slow, respectful medicine for the stone. It asks a fundamental question of us all: how can we truly learn from the past if our methods ultimately destroy the very subject we seek to understand? This ethical framework is our new foundation, ensuring that our curiosity today does not rob the future of its chance to stand in awe. A river's current could carry a burden that would break the backs of 1,000 laborers. For ancient engineers, waterways were not obstacles but open highways, offering a solution to their most daunting challenge. The strategic use of water transport turned the landscape itself into a partner. Envision massive blocks of stone, each weighing many tons, securely lashed to enormous log rafts or bundles of reeds, floating serenely down a river or along a coastline. The water's buoyancy did all the heavy lifting, transforming an impossible overland haul into a manageable, almost graceful journey. This was not a rare technique, but a cornerstone of logistics for cultures blessed with maritime access. At sites like the Hal Saflieni Hypogeum in Malta, a subterranean temple complex carved from Globigerina limestone, the proximity to the sea is a vital clue. Researchers note the existence of ancient coastal quarries where stone was likely loaded directly onto wide, stable rafts. These vessels were then sailed or rowed to the nearest landing point, dramatically cutting down the distance these heavy materials had to travel over land. The engineering of the raft itself was paramount. Nautical archaeologists point to evidence from ancient Egypt, where reliefs and surviving boat remains depict massive barges built from cedar planks, lashed together with rope and sealed with pitch. These vessels were essentially floating platforms, wide and stable enough to prevent a top-heavy stone from capsizing the entire assembly. In Mesopotamia, builders relied on buoyant boats made from bundles of reeds, coated in bitumen to make them watertight. How did they load these colossal stones without modern cranes? The answer lay in a clever use of natural forces. Workers would often construct a temporary jetty or a submerged ramp at the quarry. At high tide, the raft would be floated over this ramp. As the tide receded, the raft would settle, allowing the stone to be levered directly onto its deck. When the tide returned, the now laden vessel would float free, ready for its journey. Navigation relied on intimate knowledge of the sea. Sailors used prominent landmarks along the coast to maintain their course and harnessed predictable currents to aid their passage. Yet the risks were ever present. A sudden storm could shatter a wooden barge or swamp a reed boat, sending its priceless cargo to the depths. A powerful example of this maritime prowess is the transport of the colossi of Memnon in Egypt. These two massive stone statues, each weighing an estimated 700 tons, were quarried from red quartzite near modern-day Cairo. Egyptologists suggest they were moved overland to the Nile, loaded onto a colossal, specially built barge, and then sailed down the river before being transferred to another vessel for a journey along canals to their final destination near Thebes. The coordination required for such an operation was staggering, involving hundreds of workers on both land and water. How did ancient sailors manage the delicate balance of such a top-heavy load on the open water? Their success speaks to a seamless integration of land and sea engineering, a testament to societies that saw the ocean not as a barrier, but as the most efficient road they would ever build. The stone was never just a stone. A deep blue dolerite from the Welsh hills was not merely durable, it was a vessel of spiritual energy believed to possess powerful healing properties. For the builders of Stonehenge, the immense effort of transporting these blue stones over 250 kilometers was far more than a logistical feat. It was a pilgrimage. Each mile traversed imbued the stones with greater significance, turning their journey into a sacred act that connected the plain of Salisbury to a distant, holy landscape. This reveals a universal truth in ancient monument building. The materials were chosen as much for their symbolic meaning as for their physical strength. Granite was selected not only for its hardness but for its eternal nature, making it a bridge to the ancestors. Limestone, with its lighter color and ability to be carved, often symbolized purity and was used for temples meant to touch the heavens. The very source of the stone held profound importance. Quarries were rarely arbitrary holes in the ground. They were often located on mountains considered the abodes of gods or in riverbeds seen as the veins of the earth. To use stone from such a place was to literally build a piece of the sacred into your community. As scholar Miranda Aldhouse Green notes regarding Celtic monuments, the color and texture of stone were a language in themselves, with red ochre representing life force and dark, glossy stones channeling the mystery of the underworld. This symbolic vocabulary fueled vast trade networks. In ancient China, jade was prized not for its structural utility, but for its perceived moral purity and its link to immortality, leading to arduous expeditions to secure it from distant, often hostile territories. The material itself became a direct expression of power and authority. The gleaming white marble of Roman temples was not just beautiful, it was a political statement, a declaration of wealth, control, and divine favor that was visually distinct from the common brick and concrete of everyday life. Why did this symbolic layer matter so profoundly? It transformed engineering from a mechanical process into a deeply meaningful cultural practice. The act of building was woven into the fabric of belief, ensuring that every block laid was not just a physical step, but a spiritual one, connecting the people to their gods, their land, and their own legacy in a dialogue written in stone. A copper chisel meets granite with a sharp, percussive tap, each strike a deliberate act of defiance against time itself. This was the art of incising and engraving, a method for etching humanity's most vital records directly into the bones of the earth. On stelae like the Code of Hammurabi or the walls of Egyptian tombs, artisans transformed stone into an eternal ledger, inscribing laws, prayers, and histories with a clarity meant to outlast kingdoms. Epigraphers who study these marks note that the angle and depth of each cut were not arbitrary. A shallow, narrow groove might be worn away by wind-blown sand over centuries, while a deeply carved V-shaped channel would cast sharp shadows, enhancing legibility and resisting erosion for millennia. The process began not with metal but with charcoal or red ochre. A master scribe would first paint the text or image onto the smooth stone surface, creating a guide that could be adjusted before the irreversible cutting began. Then, holding a hardened copper chisel at a precise angle, the artisan would strike it with a wooden mallet, tapping out a series of connecting dots that slowly became a continuous, clean line. Maintaining the tool's edge was a constant necessity. An apprentice would spend hours at a sharpening stone, renewing the chisel's bite after it dulled against the unyielding granite. This division of labor was essential, with seasoned masters executing the central, sacred texts while trainees practiced on less critical borders or repetitive patterns. The pyramid texts offer a stunning example of this craft's purpose. Inside the burial chamber of Pharaoh Unas, every hieroglyph incised into the walls was a permanent magical spell, a divine script intended to guide the ruler's journey through the afterlife. How did this meticulous process ensure the survival of cultural knowledge? It fused artistic skill with an archival mission, creating a physical memory so durable that we can still read the hopes and decrees of the ancient world today, each engraved line a direct whisper from the past. Behind the shadow of every great stone stood a community, not just an army of laborers. Archaeological finds are quietly rewriting this story, revealing a workforce far more diverse than we once imagined. The graves discovered near the Giza plateau tell a particularly human tale. Here, the remains of individuals show clear signs of a life dedicated to building, yet they include women and children, all buried with honor near the monuments they helped raise. This was not a segregated camp of male workers, but a functioning society with families at its heart. Egyptologist Kara Cooney points to the vital, though often invisible, administrative roles women held, managing the vast logistics of food, textiles, and tools that kept a project like a pyramid running for decades. The labor force was a tapestry of specializations. While some teams quarried stone, others were busy weaving the immense ropes needed for hauling, or crafting the copper chisels that had to be constantly resharpened and replaced. These tasks required a wide range of skills and physical strength, drawing on the entire community's potential. The social structure itself was built for this kind of inclusive participation. Work was often organized around family or village units, where each member, regardless of age or gender, contributed according to their ability. This system provided not just labor, but a built-in support network, fostering morale and ensuring knowledge was passed down through generations within a stable environment. A striking visual case comes from Minoan, Crete. Frescoes from the island show women actively participating in ceremonial scenes that involve architectural elements, suggesting their involvement was recognized and celebrated within their culture. How does this broader view change our understanding? It transforms these ancient wonders from trophies of authoritarian power into testaments of collective, communal will. The true monument was not just the stone, but the intricate society that could organize every one of its members toward a single, enduring goal. The physics of moving a mountain begins with overcoming a single grain of sand. A multi-ton stone block rests on a wooden sledge, its journey stalled by the immense friction of earth and rock. The solution, depicted vividly in an Egyptian tomb painting, was elegantly simple. A worker steadily pours water onto the ground just ahead of the runners. This was not a random act, but a precise application of ancient tribology, the science of friction. The water, soaking into the sand or soil, created a slick, saturated paste that dramatically reduced the drag coefficient. Physicists calculating the forces involved note that this simple lubrication could cut the required pulling force by more than half, turning an impossible haul into a manageable, rhythmic progression. The types of lubricants were as diverse as the cultures that used them. In regions with abundant cattle, animal fats provided a longer-lasting, greasy surface. Along the Nile, the water itself was the most readily available tool, while in other areas, plant oils or even clay slurries were employed to achieve the same essential effect, minimizing resistance and maximizing the power of every pull. The sledge itself was a marvel of woodworking, constructed from the sturdiest available timber, often acacia or cedar, with its runners carefully curved upward at the front to prevent digging into the ground. Teams of laborers, sometimes numbering in the hundreds, were trained to pull in perfect unison, their efforts coordinated by the rhythmic beat of drums or the calls of an overseer. This synchronization was critical, as a jerky, uneven pull could cause the sledge to bog down, negating the benefits of the lubricant. Experimental archaeology provides compelling proof. Modern teams attempting to replicate these transports have found that a well-lubricated track allows a sledge carrying a 1-ton stone to be moved by as few as 10 people, a fraction of the force needed on dry ground. The efficiency gains were not marginal, they were transformative. Consider the transport of the Colossus of Ramesses Roman II, a granite statue weighing over 1,000 tons. Its journey from the quarry to the temple likely involved a continuous, prepared track, with crews constantly wetting the path ahead while teams of workers, perhaps aided by oxen, maintained a steady, relentless pace. How did builders adapt this method for different environments? In muddy conditions, they might have laid down a road of wooden planks to provide a firm, consistent surface for the lubricant to work upon. In desert sand, the water was applied more sparingly to create a firm mud, rather than a soupy mess. This was not a one-size-fits-all technique, but a responsive technology, honed through experience to conquer the unique challenges of each terrain. The true innovation was seeing friction not as an immutable law, but as a variable to be manipulated, a final, crucial step in the patient dance of moving stone. A myth is more than a story, it is a cultural blueprint. When the Epic of Gilgamesh describes its hero building the massive walls of Uruk, it is not merely celebrating a king, it is preserving the memory of a foundational engineering feat. These ancient narratives, passed down orally for generations before being written, served a dual purpose. They explained the world of the gods while simultaneously encoding the practical knowledge required to shape the human world. The scholar Joseph Campbell spent his life exploring how these universal stories provided a framework for living, and part of that framework was technical. The rhythm and repetition of oral tradition made complex information about quarry sites, material properties, and construction sequences unforgettable, transforming a dry manual into a sacred epic that every member of the community could carry in their mind. This was how a civilization safeguarded its most vital engineering principles, wrapping them in the compelling cloak of legend. The Indian architectural treatise known as the Mayamatam is a perfect example of this fusion. It does not simply list measurements, it describes the creation of a temple as a spiritual act where the precise proportions of the building mirror the cosmic order. The text uses allegory to explain tools and processes, making the knowledge accessible to artisans who may not have been literate but understood the symbolic language of their faith. A chisel becomes an instrument of divine will, and the act of laying a foundation stone is equated with establishing order out of chaos. This was not a secret code, but a teaching method that connected the physical labor of construction to a higher purpose, ensuring that every cut and every placement was performed with reverence and precision. Consider the Greek myth of Daedalus, the legendary craftsman who built the labyrinth. His story of creating a structure so complex that none could escape it may well be a mythological echo of the actual, breathtaking palace complexes of Minoan Crete, with their bewildering multi-level layouts and intricate, winding corridors. The legend preserves the awe that such architectural innovation inspired, attributing it to a semi-divine genius. What practical truths lie beneath these tales? They reveal that for ancient societies there was no separation between the engineer and the priest, between the act of building and the act of worship. Innovation was not seen as a purely human invention, but as a gift from the gods, a spark of divine insight that allowed humanity to participate in the creation of permanence. This cultural context is the missing piece in understanding their achievements, for it was this profound belief that provided the unwavering motivation to undertake projects spanning generations, turning mythical inspiration into enduring stone.